this. Okay. Yes, so there is a theorem that I promised I will do. Now we have all the tools to do it. So here is a proposition. That f from x to c be a non-constant meromorphic function and x compact. Right? And x is compact. Then I just said that we shall prove that the sum orders of a p at all points of x, this is equal to 0. And of course, this sum is finite because the orders at many points, almost all points, is 0, except at poles and at zeros, where the order is not 0. Otherwise, the order is 0, right? And you remember that we checked this formula at least in one case, right? Where, what was the case we checked it? When x was c hat, the Riemann sphere, and f was a rational function on c hat, which is a meromorphic function. And in fact, these are all the meromorphic functions, right? In that case, we checked it, but now this is much more general. So proof. Okay, so first of all, recall definition of order. So we said that order of f at p is equal to n, where n is minimum of say k's such that ak is different from 0, where f of z is equal to z minus z0. Okay, so let's try to get this. Is sum ak z minus z0 to the power k over k, right? So
does k come from?
What's that?
K goes from negative.
K goes from negative infinity to plus infinity, but because it is meromorphic, only finitely many negative terms exist, right?
Yeah.
It only goes up to finite many. And this is the smallest such k where ak is different from 0. Basically, it's the first term that's non-zero. It starts with that and then goes all the way up, right? And then that's the order of the function. And obviously, the order is negative, right?
Isn't it z minus p is equal to 0?
Sorry?
Z minus p is equal to 0?
No, okay, so what this notation means, it means that I have chosen a coordinate system and I'm writing it in that coordinate system.
Oh.
Yeah, so because p is over the manifold, it doesn't make sense to say z minus p, but we go into by coordinates to the c and then we just say z minus z0. So z0 indeed is the image of p.
Right.
Yes, under the coordinate map. Okay, so this order of p of f is less than 0 for poles, and ord p of
So
f.
suppose x is equal to c hat.
What's that?
Suppose x is equal to c hat.
X is equal to c hat?
Yeah. Then does it, for each p in c hat, does it make sense to speak of p in c as well?
You can use a coordinate system where p is represented by z. Yeah. If p is not infinity.
Okay.
Okay.
Oh.
We can do that. Yeah. Okay. So order is positive is p is a 0, and or p f is equal to 0 if f of p is different from 0. It's just the point where the function is different from 0. Okay, so this is just background, but this is the, okay. Now what we do, we are going to define, so this, we use this f, we construct this function, I don't know, we call it maybe f hat or something. So maybe we just call it capital F. This term goes from x to c hat. In fact, we are going to c hat, right? To c hat, where this f of, you see, x is equal to f of x, right? So if x is not a pole, and then f of x is equal to e infinity, which is a point on c hat, if x is a pole. Right? So we can always define this function. This f now is a holomorphic function between compact Riemann surfaces, right? F is holomorphic. So f meromorphic, of course, implies that f is non-constant and is holomorphic. Right? So we have that. Then you remember we had a concept of degree for such things. You see, we had the idea of degree. So let me recall the definition of degree. Degree of a holomorphic map between compact Riemann surfaces. Okay, holomorphic.
How do you say that capital F is holomorphic?
Okay, pardon?
How is capital F holomorphic? Because it goes to infinity.
Yeah, it goes to infinity, but infinity is just a genuine point of C hat.
Right.
So this, so infinity is like any other point of C hat. It doesn't make anything special about infinity in that case. That's go there. It's just North Pole.
Right.
So it's nothing special or strange about being infinite in this case. And then if you write the coordinate system, you notice that it comes from the definition of being meromorphic at that pole. Yeah.
Mm-hmm.
Okay, so now we have this, let's call the degree of this holomorphic map. How did we define the degree? Remember, we defined the degree by the following formula. So let's recall in general, f goes from x to y, right? We define dy of f to be sums of multiplicities at p of f. E belongs to f inverse of y, right? So we just pull back this point y in y. There are some points in the inverse, and then we just compute the multiplicities and add those multiplicities. Where now, what is multiplicity? Where multiplicity of f is defined you're using a local normal form, yeah? Via local normal form. Right, via local normal form. In other words, we showed that actually for any holomorphic function around every point, there's always a coordinate system where in that coordinate system, f of z can be written as z to the n. In that coordinate system, right? And n is multiplicity of f at p, is also called ramification index. So it means that around that point p, the function is m to 1. It looks like exactly, locally looks like the function z to the power zm.
What do we mean by like looking like zm? Do we mean that there's an approximation, or do we mean like...
No, it's not an approximation. It's by changing coordinates, it is zm. You can change the coordinates in that coordinate system, it's z to the power m. That's what it means, yeah. Right. So this is the one, right? Now, if you look at this definition, star, and this one, you notice that there is a relation actually between this multiplicity and the order of the function. They are the same, actually. So comparing the definition, you notice that. Okay, they are the same, but yeah. So comparing. Okay, this definition. So let me call this double star. Double star with definition of order. You conclude that actually order of f at the point P is exactly equal to multiplicity of capital F, where capital F is this function at P, right? If P is a zero, but notice that multiplicity can never be negative. Multiplicity is either 1, 2, 3, 4, and so on, right? But order can be 0 and can be negative also. But if you are at a pole, then order is negative multiplicity. So because if the function looks like z to the m, if it is a pole, it means that in the right coordinate system is 1 over z to the m, starts with that. So these two things, now we are going to use the theorem that we proved. Let me recall the theorem.
So what if it's a zero?
What's that?
What if it's a zero? So what if
P is, oh yeah, I didn't write it here. Maybe P is a pole. Is that what you meant?
no, sorry, what if the order is just zero?
The order at what?
P at P is zero.
When is the order is
No,
0?
what if the order is zero?
Or if the order is 0, yes, that's an excellent question. In that case, m is equal to 1 actually. Yeah, this order is equal to 0. It means that the function does not minus m is equal to 1.
So there are two cases where.
So there's that case as well, yeah.
So if f is a single pole or a simple zero, m is 1.
Yes,
And if the order is just 0, m is 1.
yes, that's true.
Okay.
Yes, okay, now let me write this theorem that I proved about those things. Recall. Okay, so now let's recall. We just showed that so this definition dy f is independent of the choice of y, right? Is independent of y belonging to y. So the way we defined it, we argued that this is a locally constant function in y, and because y is connected, then that's going to be a constant function. So, okay, so this is independent of y. Now we are going to compare this at 2 points. D0 f is equal to, if you compute at point 0, or you compute it with respect to the point infinity. For 0 and infinity are 2 points belonging to C hat. That's our y this time, right?
Is y always zero?
No. The theorem is very general. The theorem that I proved is for any holomorphic map between compact, non-constant, compact, which is a non-constant holomorphic function from a compact Riemann surface to another Riemann surface. which is necessarily going to be compact. But now I'm applying it for this case. We'll see. So there are these 2 points. So now if you just see it, so this is your sums of basically orders of f at p, where p belongs to f inverse of 0. So this is sums of orders at 0 is equal to negative sums of orders of f at infinity. Well, I mean, no, 0. And then p belongs to the inverse of infinity. So bring it to the left-hand side, you get sums of orders of, oh, no, I'm sorry, p belong and p, yeah. Yes.
Where did the negative sign come from?
Oh, the negative is because at poles you have these functions like this. But if you write this function in the right coordinate system, it's going to look like Zn. So order, it can be negative, but multiplicity is never negative.
Okay.
So you just need to introduce a negative sign, right? So you bring it to the left-hand side, you get that the sum is 0. So sigma orders of p of f over all points is equal to 0. So basically what this result says that, it says that the number of zeros of a holomorphic function is equal to number of poles counting multiplicities. So this is something, maybe a good way to remember this. So basically, the moral of the story is that number of zeros is equal to number of poles. Of course, counting multiplicities, not just, if you have a pole of order whatever, you have to count it that many times. If you have a 0 of order 5, you have to count it 5 times, for example, right? Number of poles. Counting multiplicities. So this is a nice result, right? It really gives you a relation between number of poles and number of zeros of a holomorphic function between compact Riemann surfaces. So that's quite powerful, right? Okay. Any questions? Okay. So now let me, because I like to make these analogies with p-adic numbers, so let me again make this comparison with p-adic numbers again and number theory a little bit, just a bit. So I'm going to erase this. Something like this actually happens also in the world of p-adic numbers and for rational numbers. Okay. So I've got now, so this is compared with p-adic numbers. I mean, not really p-adic numbers. I mean, with p-adic valuations. I mean, that's, I didn't introduce p-adic numbers. I just said p-adic valuation. So for A over B belonging to Q, right? So I define for any prime P, right? We define this number nu P of A over B to be equal to n if you can write A over B as P3n A prime over B prime, where P does not divide A prime or B prime. Right? So we can always extract any P power that exists, but of course N could be 0, could be positive, could be negative, right? So So n belongs to Z. Okay, so this is I argued that this is an analog of basically order of a meromorphic function. So this should be compared with order of a meromorphic function. Quite comparable to that. Okay, now what we do, we define a p-adic absolute value. So this is p to the power minus p of a over p. Just raise it to negative of that. Okay. Then the theorem is, I mean, it's a result. So lemma is this: is that product of all absolute values over all primes p times this quantity, which I put it like this, is actually equal to 1. Where this one is actually the absolute value of the function. It's the usual absolute value. So these are p-adic absolute value, that one is the usual absolute value. And the product is always 1.
So after 0, the valuation of A over B is just 0.
At 0? No.
Oh.
We always compute it at primes.
Okay.
So you just go, so primes are 2, 3, 5, and so on.
So what is it at 2? It's 2 to the raise the power of
So you look at the power of 2 in A, the power of 2 in B, and subtract them, and then that's the power of 2 in the total.
Okay.
Okay, I mean, this is not part of the complex quantum Riemann surface theory, but there is a parallel story in the world of numbers, actually, which is quite remarkable. I mean, this is very, very easy to prove. I want you to actually prove it. Once you prove it, you see that what they proved, actually, it has 0, right? So it's like log of this thing. Take log of these things, you get sums of these things are actually is equal to 0. And that's comparable to what we had. Anyhow, so that's just an analogy, but you must be a little bit into number two to understand this. Anyhow. All right, any questions?
Is that over every prime number?
Which one? Yeah, P runs through all prime numbers. So of course there are infinite number of prime numbers, but the point is that all of these guys are 1 except for finitely many primes, which are different. Because you see here, like there are only finitely many primes that divide A and B. The others don't. So in that case, you get n equal to 0. And then you raise this P to this power, you're going to get just 1. So they don't contribute. Yeah, it's like the following situation. You have all these points, infinite number of points on the Riemann surface, but only finite number of them are zeros and poles of your function.
And that product, it doesn't include the A over B infinity, right? Like,
No. This is primes. Of course, infinity is
Yeah.
not a prime, but this is infinite.
no, but like, when you have the multiplication,
Mhm.
is it for both of those terms or just the term on the left?
No, we multiply everything and then multiply it by this one.
Okay, then what?
Like them all, doesn't matter. Multiplication is associative. I don't know what you mean. Oh, I see. No. I mean, it's like this. That's what you meant, right?
Yeah.
Yeah, exactly. Yeah. And sometimes this is called the prime at infinity. Infinity is a kind of prime which is far away. Okay,
Why,
Well,
why?
let's say A over B is, sorry.
Okay.
go ahead.
So why do we consider infinity to be a prime? Because how does that,
This is a compactification of Z in a way.
yeah, but why do we consider prime not composite?
Prime or not?
not composite? Why is it not a composite number?
Oh, because it fits into this equation, so it serves our thinking, it organizes your thinking.
But like, for example, if we multiply infinity by 5, it's again infinity, right?
So that regard is, yeah, but no, I mean, there's one point, this is at infinity, and there's only one point, you just look at it as reality.
Oh, yeah.
Yeah. Yes.
So let's say A over B is 2 over 3.
Mhm.
Then,
Then only this thing exists only for p equal to 2 and p equal to 3.
so when p equals to 2, it's equal to 1 by
So
2.
is that what you mean? That's equal to 1. And okay, so and then 3 of 2 over 3 is equal to -1, and then new p of 2 over 3 is equal to 0 for p different from 2 and 3.
Right.
That's what you meant, right?
Yeah.
That's a good example. I mean, it's a good question. Yeah. Okay. So now we can prove the celebrated Riemann-Hurwitz formula that I promised to prove last lecture. So I just erase this. So there was a mistake in my statement. And when I posted my video, I noticed that I should, instead of plus, I should have had minus. I made a comment at the end of my video that's correct. So let me write it here. So this is Riemann-Hurwitz formula. So what is the formula? It just says let f from x, y holomorphic, non-constant, and X compact Riemann surface. But holomorphic number of degree D. So you just have a degree D, right? So you have a degree D map from this Riemann surface to the target Riemann surface is holomorphic and is non-constant. And then we can relate Euler characteristic of X to Euler characteristic of Y in the following way. Chi of X is equal to D times chi of Y minus some multiplicities of at P of F minus 1, where P belongs to X. So there should be a negative. So when I wrote my formula, I had plus, so this is negative. Okay, so chi of X is equal to 2 minus 2g. This is Euler characteristic of X. This is also by Euler's formula, we know it can be computed as V minus E plus F formula, right? Equal to V minus E plus F. For any triangulation with V vertices, E edges, F faces is always for any triangulation. And you remember that last lecture, I actually proved this result without this term, provided that it's not ramified. All points are non-unramified. Yeah. So this term is basically.
Sorry, what do you exactly mean by triangular?
There's only one possible definition you can think of.
Graphs.
Yeah, you just decompose your space into this disjoint subsets, where each subset is like a homeomorphic to a disk. But then you have this graph also on the boundary, but topological graphs only.
Right, right. And they cover the whole space, right?
They cover the whole space, and you show that it exists and actually
It always exists, right?
they always exist. I mean, for Riemann surfaces, actually, definitely. For general manifolds also they exist. You can always, not the triangles, but the higher analogs of like the simplicial sets and stuff. You can always do that, right?
So this is like a analog to graph theory in a sense.
Yeah, except that the surfaces are important and the way that it covers the whole thing is important. Yeah. So this goes back to Euler, as I said. Euler proved this actually. Okay, so proof. So the trick is the following. So we have to choose a triangulation for Y, which contains all. So let me recall some definitions. Branch. So what was the idea of branch point? Branch points of F. These are those points in the target in Y, which are images of ramification points, equal to the set of all F of, say, E belonging to Y, such that P is a ramification point. Okay. So these are called branch points, and upstairs we have ramification points. And so now the trick is the following. We have to choose a triangulation for the base for Y that contains branch points as vertices. But there could be more. So the idea of proof, choose. There are many such triangulations, but we just choose one. Choose a triangulation for the base that contains all branch points of F. So it contains all branch points of F, but possibly more. There could be more. Possible. So the picture that we will have is the following. Now,
But isn't that true of any triangulation of Y?
what's that?
Any triangulation of Y would contain all the points of Y. And then...
No. Okay, so yeah, you're right. I mean contain as a vertex.
Okay.
Right. That contains as a vertex. That's a good point. Yeah, contains as a vertex. Yeah, absolutely.
Okay, thank you.
So when you choose those vertices, you should make sure that branch points are you picked up, and then some more maybe you need because.
Fine.
Exactly. So now here is Y, and here is like you have some branch point like Y here, little y. And when you look at the inverse image, so as we discussed, some points could be. So here has a ramification index 3. Here is ramification index 2, and here is just. Okay. And then you can have another point, maybe, so this is Y1, Y2. Another point is just, this is not a branch point, Y2. So the inverse image are really like 1, 2, 3, 4, 5, 6. Here I just. Okay, and so on. Okay, so now what we say is that okay, so now let V prime, E prime, F prime be equal to a number of vertices, edges, and faces of the triangulation on the base of Y. of or Y triangulation. Okay. So then what we do, we just pull back this to so under F. So here is capital F. And this whole thing up here is X, right? Here is X, and again, this is F. So, and pull back. Pull back this triangulation to X. Back this triangulation to X now. Right? Okay, so now let's see what happens. In the previous case that I proved in the last lecture, we saw that the number of vertices, number of edges, number of faces are all multiplied by D because this map is D to 1. So when you pull back, if you have D vertices on the base, you're going to have D vertices upstairs because the map is D to 1.
What are the branch points?
Yes, exactly. In branch point, something funny happens. But I was talking about the case that there are no branch points. The map was unramified. In that case, everything was multiplied by D, right? So now let me give you a picture, and if you look at this picture, that will solve completely all the problems for you. So you'll see that. Okay. So so let me write it like this. To understand it, consider an example. So the simplest example I can give is the map like f of z equal to z squared from c hat to c hat. From c hat to c hat. Of course, this is a degree 2 map. And let's choose a triangulation for the base and see if we pull back, what do we get upstairs, right? Simple. Okay, so here is your X, which is C hat. And here is your Y, which is also your C hat.
Is
I'm not-
it 0 a branch point?
What's that?
0 is a branch.
0 is a branch point, and what are the other branch points? Well, you mean here? 0? Yeah, is a branch. What is the other branch point?
Infinity.
Yes, the infinity is a branch. Okay, so now let's choose a triangulation here. Okay, so the triangulation here I'm going to choose is, for example, the following. I just choose here. I just okay. So let me just okay. So what I'm going to do, I will just make northern hemisphere into 3 triangles up there. I'll just pick 3 triangles up here. So if you want, this is 1. This is okay. So let me make it 4 triangles. 1, 2, 3, 4. Okay. In the back. Okay. And now here, I also do the same here, similar thing. This goes here, this goes here, this goes here, and this one also goes here. Okay, so now let's look at how many vertices we have here. So V prime. How many vertices I've got? So okay, this is not a vertex. Okay, so here is a vertex. Here is a vertex. I have 4 vertices here as well, right? Isn't that right? So how many vertices I have here? How many vertices? 1 and 1 is 2, and plus 4, I've got 6. 6 vertices. How many faces I have?
8.
Hmm?
8.
How many faces we have? Yes, we have 4 down and 4 upstairs, 8 vertices altogether. Faces, sorry. And how many edges we have? How many edges we have? E prime? More than that. How many edges? Look, you have 4 edges down here, 4 edges up here, and also 4 edges on the equator, because these are also part of the edges. I'm counting them as different faces. 12. Oh, then because I counted these are as separate faces, so I have to count 12. Okay. So now I pull back. So this is F. I pull back this by F inverse, then I'm going to get something here. So now the question is, so you're going to get a triangulation here. Okay. You have triangulation there. So how many now? So V is what? E is what? F is what? So what happens is that when you pull back, the number of edges is going to be multiplied by the degree, basically. In general, it's going to be D, number of edges down here, which is E prime. Number of faces also is going to be D prime, but number of vertices is more complicated. It's not going to be multiplied because these points, this point and that point, right? They only have one inverse image. At those ramification points, you only get at those branch points. When you pull back, you're not going multiple of that. You're going to get something less possibly. And here indeed we have to get less. But these 4 other points is going to be multiplied by the degree of the map, which is 2. So you're going to get 8 vertices here. So 4 here, 1, 2, 3, 4, 1, 2, 4. So 8 here, and this 2. And but then vertices, I mean edges. Etc. Okay, so there is also downstairs. Okay, so let me write the general formula now. So in general, edges and faces, number of edges and number of faces gets multiplied by the degree. Which is degree of F. And you can understand why this is the case, because each edge actually comes through points that are where the function is not a branch point. And around those branch points, the map is D to 1. So you can see that there should be D times as many edges and D times as many faces and so on, but not for vertices. Okay, so now the general formula that I wrote, I can organize it like this. So I'm going to write like this. Okay, so I'm just going to say this. Yes, so my notation here is the opposite. So I'm going to use V for this one. And I'm going to use D prime, E prime, F prime. I just chose my primes for here rather than over there, to be consistent with my notation. Okay, so now let me write the general formula. So this is supposed to be an example. But this just stick to this picture actually. Can I write? So now, if you look at this picture, then you can just say in general. We can just write E prime equal to D E, F prime is equal to D F, but V prime is different from D E. In fact, V prime in fact is equal to D1 plus a number of ramification points. Okay, so what is V prime? So this V1 is a number of branch points or non-branch points. Bro, and non-branch points. Vertices. So, and number of ramification points is equal to, I just write it as sum P belonging to branch points sum, I just write it like this, sum 1 and then X belonging to F inverse of P. You see, here, these are the branch points. When you pull back, you're going to get things like this. So these are the only vertices that you get. But if you have a non-branch point as a vertex, then you get as many multiples of D for that. So this is the composition that we use, and this is just a simple move. Then I just write this sum in the following way. So this is equal to sum P belonging to B. And then I've got sum 1 X belonging to F inverse of P. And then so I want to subtract minus n and add plus n. So this is just do this for now. Then now I'm going to write it in the following way. So this is equal to sum P belonging to B, and then I've got sum X belonging to F inverse of B, and then I just write 1 minus multiplicity of F at X, 1 minus multiplicity, and then plus F. So I just pull this minus 1 and change sign. So this is equal to minus. Now sum P belonging to B, sum I get multiplicity of F at X minus 1 plus sum N E belonging to these branch points. So far, I mean, what we get is the following: V prime is equal to DVO. I'm changing D to, so sorry, this is D. I'm sorry.
Professor, are you missing an open parenthesis?
Huh?
Are you missing an open bracket before the second summation?
Yeah, this is,
No, in the next line,
here.
yeah. Is there a missing open bracket?
Yeah, this goes all the way, yes.
Okay.
That's what you meant, right?
Yeah.
Yeah, because, oh, no, this is, sorry, this is the one. I should put it like this. Okay, so then what we get, oh yeah, by the way, I should change N to D because I chose for my degree D, not N. Yeah, here is okay. So you get V prime, which is equal to D V1 plus what we had, the plus number of ramification points. It comes out equal to a D V1 plus sigma N. I just pick it from there, D belonging sigma D again. Over branch points minus some multiplicity is f x minus 1, and this is x belonging to x. That's what we wanted. So then substitute these values, okay? Sub these values. I mean, there is this value, and this value. So sub in star, double star, equal to star into formula. I just have to be careful again with my, in formula, Euler characteristic of x is equal to, so yeah, I'm just using prime for the domain. So I just use v prime minus e prime plus f prime, then you get, this is equal to the Euler characteristic of y minus some disturb here. What this is. Okay, so I just use E for my notation, but I just use it. Explain. I mean,
What we do, that is the characteristic.
oh, there is D exactly, yeah. So, thank you. Yeah, this is excellent. Yeah. Yeah. So the idea proof that the real trick is to choose the triangulation on the base, on the target space rather, base you can call it, to contain branch points as part of the vertices. And also notice that if you pull back, the edges and faces gets multiplied by D, but not vertices, because vertices can be branch. And they are not D to 1 at branch point, or less than that, because several things can collapse. But yeah, so this is a very important formula. It has amazing number of consequences. So I would say in elementary aspects of Riemann surface theory, this is the most important formula. The next level is Riemann rock, which is much more, but I mean, yeah. So let me write it. Are there any questions? Or? So the important thing is to be able to use it in many contexts, in many applications. Yeah. So I think now we stop for a break. Good idea to stop for a break, and then I will write down some applications of this. Okay, so let's pause.